So when we talk about the carboxylic acid, so this is basically your carboxylic acid, which has a carbon double bond oxygen, and it is single bond oxygen, which is further bonded to hydrogen, right? Ignoring this hydrogen, so basically the carboxylic acid has got carboxylate ion, which has a negative charge on it, right? And this carbon double bond oxygen, this double bond, it keeps on shifting between this oxygen and between this oxygen. So we can say that the carboxylic group itself, or the carboxylate ion, is again, it's going to form a resonating structure just like benzene. Okay, so when it is going to resonate structure, so when it is going to resonate, it will be forming a ion where a double bond will be between this oxygen and a single bond here with a negative charge, or this particular double bond can again shift, to this oxygen as well. Fine, this oxygen as well. So we will have another structure where it is going to be single bonded with this oxygen, forming a negative charge on it, and a double bonded. And these two structures, they keep on resonating, they keep on changing into one another, giving us a very stable ion. And that stable ion is because the negative charge is spread over structure, right? So here there is a half double bond between this oxygen, okay, and half double bond is there between the two oxygen which is bonded to carbon. So the electron flow gets delocalized between these oxygen, and that gives the stability to this particular ion. So this ion is actually known as carboxylate ion. Okay, and because this ion is highly stable, and that is the reason this will not get combined with the H positive ion, which heterolytically break down, right? So it try to remain in the ion form, and that is why the carboxylic acids, they are strongly acidic nature, because they are proton donors. So this stable ions have a difficulty in reforming into the undissociated molecule, that is RCOOH, and because they are giving away the proton easily, so that is why they are acidic in nature. I hope this is clear. Fine. Now, moving ahead with this. Now, we are moving on to the carboxylic acid now, acid derivatives now. In the last class, we have studied about the carboxylic acid and the physical properties. We are talking about the carboxylic acid derivatives. So among the derivatives, we have the acid halides. The acid halides are also known as acyl chlorides. Okay, halide means they can be, this X can be your chlorine or bromine or iodine. Basically, these are your acyl. We generally call them acyl chlorides if this X has been substituted by chlorine there. So, right? And they are very reactive, very much reactive than carboxylic acid. They're soluble in water, they are very volatile. So we'll talk about it in detail later on. Then now here what is happening, why we call them derivatives? We are calling them derivatives because this OH has been substituted by a halide, or basically we're saying that chloride. So if it is a chloride, we are calling it acid chloride or acyl chloride. Generally we call them acyl chloride, right? So this is first derivatives. Now from this carboxylic acid, we can also get acid anhydride. We generally don't go for acid anhydride. Then the next derivative is an ester. We have already studied about the esters a lot in our O levels and in AS level. And then the next derivative we have, these are said to be nitriles. They are also acid halide, right? And then we have one more acid derivative. These are basically amides. Now amides are RC double bond O and NH2 being added to it. So again, the OH is being substituted by the NH2 amine group. So that is why you call them amides, right? Now, when we talk about their comparative reactivity, when we talk about their relative reactivity with the carboxylic acid, we say that the acid halides are much more reactive than your carboxylic acid. Okay, when we compare their relative reactivity, we say that the acid halides, they are the most reactive, right? They are the most reactive. Now, the reason them to be more reactive is, look here, if I draw the acid halide or acyl chlorides structure wise, so I will be drawing it like this, right? So that means the carbon is between the two electronegative element. Oxygen is one electronegative and the chlorine is more. So basically they will be pulling the electron toward themselves. When they're pulling the electron toward themselves, so carbon is going to be partially positive. Now this acyl chloride, they actually undergo the reaction, the nucleophilic substitution. They undergo the reaction because we have nucleophilic substitution reaction. We have a carbocation being developed here because it is bonded between the two electronegative element. So they will be partially positive and these ends are going to be partially negative because they are electronegative. So automatically the nucleophile, which has either the lone pair or they are partially negative, right? So these are going to attack the carbocation, and the same is going to be the case of carboxylic acid. But here we have only one electronegative elements, or we have the electronegative elements. If we talk about oxygen, the two oxygen, this carbocation is between the two oxygen. Whereas if we talk about the chlorine is definitely more electronegative. So this carbon is acquiring a more prominent positive charge. So it will be attacked more easily by the nucleophile as compared to the nucleophile is going to attack this carbocation, right? So we say that this acyl chloride or acid halides are far more reactive than your carboxylic acid. Okay, so if we talk about their reactivity, on comparing their, if we talk about their relative reactivity, carboxylic acid derivative we have talked about. So first comes your acyl chloride. Okay, first comes your acyl chloride, then comes your carboxylic acid. Okay, and then comes your esters, and after esters you have your amides. Now the reason why esters and amides are less reactive than carboxylic acid, we have studied about the electron donating groups. Remember, electron donating and electron withdrawing groups, right? So among the electron donating group, we have our alkyl groups and we have our NH2 groups, right? Amine group. So in the case of an ester where our alkyl group is bonded to C double bond O and O and R. So this is another alkyl. So alkyl groups are electron donating. So when they will be donating the electrons, they will be making this carbon less polarizable. And same goes with the amides as well. So when the amide, you look at the structure of the amide, the same way this amide, they are electron donating. So they will be making this carbocation less polarizable. And that is the reason their reactivity is far less than the reactivity of carboxylic acid. Okay. Now, in terms of acidity, whether they're acidic in nature or they're neutral in nature, we'll say that the acyl chlorides are also said to be neutral and the amides are also be said to be neutral, whereas the carboxylic acid, they're acidic. Now, the reason is acidic means they are proton donors. Whatever the substance are proton donors, they're said to be acidic, right? And the carboxylic acid do have the OH there. So they donate the H positive ion, they are proton donors, but there's no such protons in the case of acyl chloride or amide. So that is why they are said to be neutral in nature, whereas the carboxylic acid is acidic in nature. Till here it's clear? Okay, our focus right now is on acyl chloride only. So we are just going to talk about the carboxylic acid derivative, which is acyl chloride, or we basically call them acid halides, right? So this is how the acyl chloride is being formed. So acyl chloride are formed from carboxylic acids. So when the carboxylic acid what do you call it, OH is substituted by the halide, we get acyl chlorides or we get acid halides, right? Now, in comparison to the carboxylic acid, they're talking about the physical properties. So when you compare their boiling points or the relative molecular mass, so this is how it is. So the relative molecular mass, when you talk about ethanoyl chloride, this is how you name them. So acyl chlorides are always named as ethanoyl chloride because it has two carbon in it. So the compound which is being formed from propanoic acid will be known as propanoyl chloride. The one which is being formed from butanoic acid will be called as butanoyl chloride. So when you talk about their respective, now we are coming back on to the acyl chlorides. The general formula for acyl chloride is CnH2n plus 1 COCl. We have the carboxylic acid general formula as CnH2n plus 1 COH. So basically OH has been substituted by a halogen, and that is why we have the acyl chloride here, CnH2n plus 1, and we have COCl. So this is the general formula for an acyl halide or acyl chloride specifically. And their names, we add the suffix that is noyl. So ethanoic acid will be giving us ethanoyl chloride. So here we had, what do you call it, CH3COOH. So OH has been substituted by Cl. Then the propanoic acid will be giving us propanoyl chloride. And similarly 2-methyl propanoyl acid, because this is acting as a branch here. So we will be having 2-methyl propanoyl chloride because OH has been substituted by Cl, and this is a benzene, right? If you have a benzene ring and the chlorine attached to it, so this is benzyl chloride. Now, one more thing which I want to explain it here, we have the three categories of halides, right? Now, in AS level, we have studied about the alkyl halides, okay? Then here we have studied, this is an example of aryl halide. This is an example of aryl halide. So we will be talking about the aryl halide as well. And this is the category which come in between, that's your acyl chloride. So all of them are basically the halides. So they have a little similarity and the differences too. So you should be knowing there what is the difference between these all three. And their reactivity is very different, right? So if I talk about the alkyl halides, then the alkyl halides are basically RX, where exactly an alkyl group is directly attached to the halide. Like for example, I have CH3Cl, or I can say CH3CH2Cl. This will be known as chloromethane, this is chloroethane, and so on, right? So these are alkyl halide which undergo nucleophilic substitution, and we have done them in detail, and we say that they are an excellent intermediate compounds from which we can form lot of compounds from different homologous series. And we in the past papers in A2 we are too much relating to alkyl halides. They are very reactive. Then after that, we move on to the acyl halides. These are your carboxylic acid. They are your carboxylic acid derivatives, right? Where the CO is also there. These are carboxylic acid derivatives, right? So we have seen that their formula is CnH2n plus 1, and CO is very much there, and Cl. So their general formula is RCOCl. So CO group, carbonyl group is also there. Then we move on to the aryl halides. Aryl halides is another category where the benzene ring is attached to the chlorine. Okay, so if we talk about their reactivity, then we say that the aryl halides are the least reactive, and followed by alkyl halides, and the most reactive are acyl halide. When you talk about the alkyl halides, though, we know they undergo the nucleophilic substitution reactions. So the carbon become partially positive because of the electronegative chlorine being attached. So the nucleophile, whether it's in the form of ammonia or it's in the form of a water, they attack the carbocation, and the nucleophilic substitution take place in alkyl halides that we have seen in AS. Now, when we compare with an acyl halides, acyl halide, we have a carbon in between the two electronegative element, oxygen and chlorine. Now, they being electronegative, they are pulling the they're pulling the electron towards themselves, making the carbon more polarizable, having a more stronger positive charge. So in comparison to alkyl halide, the acyl halides are much more reactive. Now coming to aryl halides, that is your benzoyl chloride. In this case, what happens? The chlorine has the lone pair of electrons, and it feeds the lone pair of electrons are fed into the delocalized ring. Okay, they are fed into the delocalized ring, and they are increasing the charge density, the negative charge density of this ring increases. Okay, density of this pi ring is basically increases. Fine. And that is the reason this bond of benzene ring and the chlorine, it becomes very, very strong. Okay. And they basically undergo electrophilic substitution reaction. So it becomes very difficult to substitute the chlorine with any other group. So these are said to be the least reactive, because this bond, because its electrons are extended into this delocalized ring, so the bond become very, very strong. So it becomes very difficult to substitute chlorine with any other group. So they are, when you compare them as 1, 2, and 3, we say that the acyl chlorides are said to be the most reactive. Then comes your alkyl halides. Okay, I mean basically the chloride only. And the least reactive are going to be your aryl halides. Okay, so they are least reactive, and this is the reason. So they often ask in the past paper a 1 mark question or 2 mark question asking about the relative reactivity between any two or any three of them. Okay, so this is what we have done right now. So we should be very clear that whether examiner is asking about alkyl halide or they're asking about the acyl halide. So this is the general formula. The CO has to be there. And whenever they're combined, directly they're connected to the chlorine. So they will be getting an aryl halide, right? Now, if, for example, if we have a compound, something like this, let me know which category it belongs to. Is it category 1, alkyl halide, or acyl halide, or it's aryl halide? Why? Because this particular chain, the aliphatic chain, has a chlorine attached to it. This chlorine would have, if been directly attached to this benzene ring, then it would have been aryl halide. But now, right now, it's a part of the chain, the aliphatic chain. So that is why we will be treating it as aryl halide. Okay, am I clear? Now, moving ahead. Now moving on to the chemical properties of your acyl chlorides. So when you talk about the chemical properties of acyl chloride, again, they are, as we have already studied, that they are far, far more reactive than your carboxylic acid. Okay. And they can easily get hydrolyzed. As I already told you, that the acyl chlorides, they can easily hydrolyze, even they combine with the moisture present in the air. So they are supposed to be kept in the dry condition. So acyl halides, whenever they undergo a chemical reaction, there should be a dry conditions prevailing there. If there is a moisture, then automatically, instead of that reaction taking place, they will undergo a process which is known as hydrolysis. They combine with water. So on hydrolysis, they will be giving you a different compound than what was expected over there. So now let's talk about the chemical properties of acyl halides. Okay. So the acyl halides, as I already told you, that they undergo nucleophilic substitution reaction. Okay, they will be undergoing nucleophilic substitution reaction because the carbocation is very much positive. So the nucleophiles, the type of nucleophiles which can attack the acyl chlorides are, we can have a reaction with water. So water can be one nucleophile which has the two lone pairs, and when they react with the water, they will be producing your carboxylic acid. Okay, they will be giving you the carboxylic acid. So when an acyl halide combined with water, they will be giving you carboxylic acid back again. And similarly, there can be a reaction with an alcohol. So reaction with an alcohol, because they will be undergoing a hydrolysis producing carboxylic acid. So carboxylic acid and alcohol, when they combine together, what do they give? They give you esters. On reaction with an alcohol, they will be forming an ester. Similarly, we have another nucleophile that can be your ammonia. Ammonia also has a lone pair. Or with amines. The amines are what? They are with an alkyl group with NH2. We have a primary amine, we have a secondary amine, we have a tertiary amine. So with ammonia or with amine, the amine also has got the lone pair on the nitrogen. With the amines, they will be forming the amide. So what was the difference between amine and amide? Amine was alkyl group attached to NH2, and the amides were the carboxylic acid derivatives where the OH was substituted by NH2, right? So this is the general formula for amides. So when they combine with the carboxylic acid, either ammonia or amine, primary, secondary, or tertiary, they will be giving you amides. And these amides are again primary, secondary, and tertiary depending on the type of amines they are reacting with. Okay. So these are going to be our three basic chemical properties. These are basic three chemical properties which are basically shown by acyl halides. Okay, so let's start with the mechanism first. Okay, so let's talk about the mechanism. Now, when the examiner asks you about the mechanism, it can be with water, it can be with amine, it can be with any other nucleophile, but we very clearly know that the mechanism is going to be nucleophilic substitution reaction. It's going to be with the nucleophilic substitution reaction. Okay, mechanism. So now, for example, if I have an alkyl halide, if I have, sorry, acyl halide, then my general formula for acyl halide is going to be R, C double bond O, and I will be having Cl. Now, these two being the electronegative, so what will happen? The electron will be pulled towards these two electronegatives. So basically, when a nucleophile come and attack, this is going to be a partially positive carbocation will be formed here. This is a negative charge. So when a nucleophile with a lone pair, okay, let's say it's water or it's ammonia, your alcohol, this is a nucleophile, right? So when it come and attack the partially positive carbocation, right? So what will happen eventually, because it's already satisfied with the four bonds between a carbon is satisfied. So what will happen? What will happen? The deformation of this double bond will take place, and what this double bond will break, and it will form a single bond, right? So we'll be having an intermediate that's going to be with the carbon in the center, alkyl group here, and we will be having Cl, and nucleophile will get attached to it along with hydrogen, and this oxygen has basically become a negatively charged, right? Now, after this, what will happen slowly and gradually when the nucleophile get added, the pi bond between the carbon and oxygen breaks. Okay, the pi bond between the carbon and oxygen breaks, and the oxygen acquire a negative charge that we have already shown. Okay, now further, the nucleophile donates a clone pair. It weakens a bond between this hydrogen, and this hydrogen eventually breaks down. Okay, the hydrogen, it breaks down. Once this hydrogen breaks down, so this hydrogen and this chlorine also automatically it breaks down, right? The intermediate loses the proton and it loses the chloride. So what will happen? HCl will be reforming here, okay? And eventually, when this chlorine will be dissociating from this intermediate, the double bond of this oxygen will be reforming back again. So we will be having the compound that is going to be R, C double bond O, and the nucleophile, whether it's a water or it's ammonia or it's an alcohol, that will be connected. So because the hydrogen from a nucleophile heterolytically breaks down, this chlorine breaks down from the carbon, so they reform to form HCl, and the oxygen bond, double bond will be reforming to give us this. Okay, so this is going to be, this is actually an addition part is taking place. And then what is happening here? Substitution is basically. So it's an addition and basically elimination. Okay. So whenever the addition and the elimination part take place, we also call it condensation. So basically, remember when we were talking about the condensation polymerization? So basically the two monomers, they combine together by eliminating one water molecule or ammonia molecule one small molecule was eliminated, and we used to call it condensation. So whenever an addition and the elimination of a simple small molecule take place, we also call it a condensation. So this is a nucleophilic substitution reaction taking place because the attack is by the nucleophile. And when the attack is of the nucleophile, so first of all, the nucleophile adds, and later on a simple molecule, it eliminates. So it can also be called as it can also be called as addition and elimination, or it can be called as condensation reaction. I hope this is clear. Okay, now let's take a specific example and we go for it. Okay, so let me show you the hydrolysis, how the hydrolysis take place and how the carboxylic acid is reformed on the basis of hydrolysis. So I'm taking the mechanism for specifically for hydrolysis, where an acyl chloride combines with the nucleophile, that's water, with the two lones pair of water, forming carboxylic acid. Carboxylic acid, this is a general equation I'm writing down, along with HCl is given out, right? So I'm taking an example of ethanol chloride only. So let me draw the structure. So first of all, I have an ethanol chloride with the carbon double bond oxygen and the Cl there. So basically what will happen here, this is being 2 electronegative. So basically the electron is being pulled here. And when I have a water with the two lone pair of oxygen, so this is my water, so it'll get joined, this is formed the carbocation, so this is going to attack the carbocation, and eventually this double bonded oxygen will the oxygen this double bond will break, and this is going to be a single bond. Now all this is going to create an intermediate where an addition and elimination both will be taking place. The reason is because in the case of an alkyl chloride, we will have CH3Cl only, right? In this case, we have CH3COCl. Remember, this is CO part. And
Okay.
COCl is coming from ethanoic acid. We have CH3COOH. So this OH has been eliminated and Cl is in place of that. So whenever chloride is being formed by the substitution of OH of an acid, we call them acyl, right? So remember, don't forget that this has a C double bond O as well. Okay, fine. Is it clear now?
Thank you.
Let's make an intermediate CH3C, and this is going to be water being added here. So eventually, oxygen is with a negative charge, right? It has a lone pair here and the Cl. Now here in this intermediate, the chlorine, this bond will break down. This bond is going to break down, okay? And eventually what will happen? This again is going to break up because hydrogen has to be lost in order to form an HCl. Agreed? So this is how the electron will be, and this is going to form a double bond again. After having these changes, we will be having the compound that is going to be CH3, C, and then we have a C double bond being formed here. Okay, this is CH3, this is reformed, this is C double bond O, and then we have O and H being formed. So this is basically your ethanoic acid, COOH. No, I think I made one mistake. So help me out. What mistake have I made? Yes, I should not be having this H over here. So this is just CH3, and same goes for this carbon should be there. So this is CH3 and C double bond OH. So this is how I'll be getting my ethanoic acid. This is the ethanoic acid and the HCl being formed. So this is the mechanism for hydrolysis. Is it clear, beta? So I have shown all the arrow moments, I have shown all the lone pairs, I have shown all the intermediate. This is an intermediate, so this is how you'll be showing the nucleophilic substitution reaction for the nucleophile, for the acyl halide, okay? Now this hydrolysis can take place with the OH ion or with the water. Both of them can act as a nucleophile, and they will be giving you On hydrolysis with them, you will the acyl when the acyl chloride when reacts with either one of them on hydrolysis, it's going to give you the carboxylic acid and it's going to give you HCl there. Okay. Now, if chloroethane OH minus because no. It will be reacting with NaOH, then NaCl will be formed. Okay. So if it is going to react with an alkali like NaOH, then HCl will not be formed. In that case, you'll be getting NaCl. With water, you will be getting HCl. With NaOH, you'll be getting carboxylic acid and you will be getting NaCl. That's okay. So if we have a chloro now coming further, if this we know that the alkyl halides are also undergoing the nucleophilic substitution reaction. Okay, isn't it? So when the alkyl halides, they were undergoing the hydrolysis reaction either with water or with NaOH, right? They were giving us alcohols, wasn't it? And along with that, they were giving us the similarly either HCl or whatever or NaCl, right? If the NaOH was there. Okay. Similarly, with the acyl halides, in the case of acyl halides with the water or with NaOH on hydrolysis, this time we'll be getting carboxylic acid. So you should be very clear about the product. Carboxylic acid along with HCl or along with, if we are taking NaOH, then with NaCl. Okay, so these two reactions you should be very clear. So now let's see if we have a chloroethane, that is your alkyl halide, or you have ethanol chloride, or you have a chlorobenzene, and they react with water. They it is observed that the acyl chlorides are hydrolyzed more easily, as I already talked about their reactivity to be relatively maximum. And then comes your alkyl halides and the aryl halides. As I already have initiated, I've already introduced this aryl halides. They will never undergo, these aryl halides, they will never undergo hydrolysis. Okay, why they will not undergo hydrolysis? Because this benzene and chlorine bond is extremely strong, right? So they will not get hydrolyzed under any scenario. Fine, is it clear? So if you talk about their hydrolysis, so the acyl halide, they will undergo the hydrolysis at room temperature. The alkyl halides, they need heat and reflux, and the aryl halides will not react at all. So if we compare in the term of hydrolysis itself, hydrolysis comparison of alkyl halides, acyl or aryl, we'll say that the acyl halides, their reaction, their hydrolysis is taking place at room temperature pressure, forming carboxylic acid. And alkyl halides, why it's getting erased? Alkyl halides, they will be giving you alcohols when you're going to heat and under reflux condition. And aryl halides, there is no reaction. Agreed? There is no reaction. Okay? So we wrap up today's class here only, because when I have to explain further, so the other reactions I have to take longer time. So I'm ending today's class here.